connecting this. So this is one way of converting a context-free grammar into a push-down automaton. And as you remember, there is another way for doing this, which starts by, which does not need to add the first S. So give me a second so I can paste it for you. And then meanwhile, let me deactivate the waiting room. That's it. So we have two different, it's the same. Sorry. Okay, here it is. Okay, here it is. So the first one would correspond to an LR parser, which is also called bottom-up parser, because we are adding onto the stack as we are consuming symbols. We need first to read the symbol from the input, and also we need to pop it out from the stack. The other way for building this is, remember there is a hash missing here. The other way is to read a symbol from the string, and whenever we want to read it from the string, then we are going to add a symbol also into the stack. So remember that we have like two different options. One is shift, another one is reduce. That would be for LR, as you have been learning until now, and both of them are equivalent. What I want to state today is that these two methods for building a push-down automaton from context-free grammar are completely equivalent. However, when we implement a parser, an LL parser or an LR parser, then we have some difference. So to try to be clearer, these machines assume that order does not matter, that the order in which we apply these rules or these rules does not matter. Remember that these are machines that are inherently non-deterministic. Both of them are non-deterministic machines. So this means that we need to explore all the possibilities that can be used to accept a string. And only when we have used all the possibilities and we are not able to end in an accept state, then we say we reject this string, that the string is not accepted. So we developed, or we studied several ways for solving this problem by using the LL parsers or LR parsers. These have to do with the implementation, the particular implementation of this. So whenever you see these diagrams, this is kind of a theoretical machine. This is like more abstract or in an upper level of the theory, because we do not care the implementation itself. Is as we said before, like saying it's like a declarative statement. When you do a declarative statement, you don't care how it will be executed or in which order. You just need to take care on what are the the results, how different rules can be interpreted. So this, you can regard that as a set of rules that must be accomplished in order to see if we can reach or not an accept state. So whenever we have this kind of problems, we can have a very high complexity. In this very high complexity, we may suffer of very slow. I hope you can listen to me. Okay. So whenever we do this without taking care of the implementation, we can get into a very high complexity. And as we said before, these kind of things are highly used for compilers, particularly at the syntax level. And if you can imagine, if we have a very complex language of thousands of rules, then parsing them by using these methods without a parser, an appropriate parser, then it can be very, very slow. So the LL parsers, the LR parsers we saw before, try to deal with this issue. So, however, we saw some limitations, and that's what I want to tell you today. Remember the hierarchy of languages, being the simplest of them, the regular languages. That these languages are processed by deterministic finite automata. And then we have here a superset of them, which are context-free languages. We have been seeing this several times, so this is not the first time we see this. However, please remember that whenever we try to parse a language with an LR parser, we are only accepting or are being able to accept a subset of the context-free languages. So these are the languages that are acceptable with an LR parser. And if we want to use an LL parser, then we restrict this even more by using LL parsers. An example of these languages, we have already seen them. A very suitable LL parser that is a language that is not regular and can be parsed by using an LL is the famous XNYN. Let me be sure of this. No, that's not true. Let me just check it so that I don't say lies to you.
Yes, in the previous session, you told us that that regular expression x and well, the expression that you write previously was not possible to resolve with LL.
Yeah, right. So this would be a suitable problem for an LR. So that will be here, YN. Yes, and also there are some other languages that are here that are context-free language, but not suitable for an LR, and that would be the union of XN, YN, and XN, Y2N. Yes, so now help me find a language that is suitable for an LL parser, and it is not a regular language. Who can tell me one example of this? Well, by following our examples, what about the Zaza? We were able to build a proper LL parser, and we were able to build it, you remember? So that would be S, Z, M, N, Z, M, A, M, A, or Z. Let me write it more simple like this. This is an or N, B, N, B, or Z. So just to make it more compact. Remember that this or means that this is repeated, and it implies that M can be this or this, like using a little bit of Backus-Naur form notation. Okay, so let's add here another example of regular language, X, M, Y, N, and just to be formal, M and N belong to natural numbers. So here we have several examples of languages that can be regular, like this one. Please note that M and N have no relationship, so it's equivalent just as a clean star. And then we were able to accept this language, which is the grammar that produces the Zaza string and the family of strings. And of course, we were able to build an LL parser. In this case, it was suitable to use an LL1 parser because we need to see only one character ahead, and then we can disambiguate this, the application of these rules. And then we saw an example of language that cannot be processed with an LL parser, because in this case, we need to see an infinite number of X before we know that we will have exactly same number of Ys. And because of this particular language is not suitable for using an LL, but we need an LR parser, yes? So we, as a homework, you built a parser for this language, an LR parser for this language following the appendix, and you were able to do so. And finally, we saw a language that cannot be parsed by an LR parser, which is this language, which is exactly this one, but the union with this one. Why? Because you can imagine like this is like seeing this string from the right. And if we arrive from the right, it's very easy to know if we how many Ys we will have, and then we know which one we should apply. However, in this case, if we arrive from the right side, then we cannot know if we will have exactly n or 2 times n the number of Ys. So this is why this is not possible to be analyzed by an LR parser. So these are the canonical examples, well, particularly this, and this. Perhaps this is not so canonical, but it's an example of a language that can be parsed with an LL1 parser. And you can see that by having to use a particular method for parsing restricts these languages. Now, I want to insist that for these two methods, different methods, they both have all the whole power for analyzing the context-free languages, both of them, regardless of the way they are built. So they are connected to the parsers, as we saw before. These are connected with them. However, they do not disambiguate the order of the rules. If you don't ask them to be deterministic, then you have all the power of context-free languages, which is, but in other words, that context-free languages are non-deterministic. And also, push-down automaton are not non-deterministic. If you want them to be deterministic, actually you will have the LRK parsers. So these LRK parsers are equivalent to deterministic context-free languages. So with this, we can see that if we want a language to be deterministic, then we are restricting the power of context-free languages. We are within this set. Or, put in another words, there are languages that need to be non-deterministic in nature. And let me give you an example, another example of this. Well, first I wait for you a little bit to synchronize. Okay, so you know what a palindrome is, right? Can some of you tell me what a palindrome is?
It's
Yes,
a
it's sorry.
go. Okay, it's a word that if you read from left to right and right to left, sounds the same or it's the same.
Yeah, right. Like you say a word, well, it can be Anna, like the name Anna, or it can be also a phrase, right? Like Anita Lava Latina. Maybe I don't know palindromes in English. Latina. So if you read backwards, you can see the same Anita Lava Latina, which means Anita washes the bathtub. For sure, there are some English palindromes. I don't know if you know some. I cannot remember one right now. Another one is Dávale arroz a la zorra el abad. And you can see that is Dávale arroz a la zorra el abad, meaning the priest was giving rice to the fox, which is a little bit of nonsense, but well, you can imagine some very remote place like a monastery in the middle of nothing, and there are still foxes, and the priest likes to feed them, like San Francisco or something like that, right? Okay, but that's with a lot of imagination. So for our languages that we will be studying, we will stay into our limited alphabet, but of course we can use a more complex alphabet, but we will use only X and Y. And if we use an alphabet consisting only in these two letters, then a palindrome would be a string that can be read exactly the same forward and backwards. So we can say, for example, XYX or X, XYXX, or even a little bit more complex, let's say YXY, and again YXY. And in all these cases, you can see the same phenomenon is observed. You can read the string the same forward and backwards. And also you can see there is a point of inflection in these grammars. For example, here it's in the middle, and also here you can have it in the middle, and here you have it not crossing any symbol. So we will have two types of palindromes, those that are odd length, which are like these ones, or these ones that are even length. In this case, length is 6. In this case is 3, and this is 5. So for the purpose of simplicity, because we can build also a recognizer of odd length palindromes, we will build a even length palindrome recognizer. Because we have a stack, this is pretty easy, because you can see our problem will consist only on adding this onto the stack and then removing this from the stack exactly in the reverse order. So this is what stacks are very good for, right? So push and then pop on this. So it will be quite simple. You can try it in your notebook if you want. So I'll give you 1 minute so that you can try to build a pushdown automaton that can recognize palindromes. Remember to add the hash at the beginning because you will need to verify at the end that you successfully removed the hash. When you have your solution, please show it to me. Oscar, okay. Right. So you are accepting x for each x. You add an x into the stack, and then a y, you insert an y, and then you do this magical jump with a lambda transition, and then start consuming x and y. And finally, whenever you are ready to extract the hash, then you finish into an accept state. Yes, very good. Well, that's the correct answer. Maybe there are another ways for solving this, but this is correct. And well, we will comment on that afterwards. Cesar has raised his hand. So, okay, Cesar. Yes, very good. So this is the same one as Oscar, so it's correct as well. Thank you, Cesar. Oksana, yes, I see you are adding and removing x and y in the same state. However, please note that when you do that, let me copy your automata here so that I can explain what's happening. You did something like here, adding your hash, right? And then here you allow, whenever you have an x, you plan to add an x as well into the stack. And here, whenever you have a y, you plan to add a y onto the stack. And the reverse or the contrary mode will be whenever you see an x, you will remove the x from the stack or the y from the stack, right? So this looks like your solution, right, Oksana? Did I copy it properly?
I think that one, when I'm reading X, I'm pushing X. That is correct, but yes, but loops on the down, no, I don't have those, I think.
Okay, can you show me your answer again, please? Thanks. Maybe I put them, the ones that are below, I put it at the upper part, right? So, okay, let me try to do it the same as you. That's correct, right? The lower part.
Yes.
The upper part, I'm not sure if I am understanding properly. You did something like this? Or it's different?
It's different. I'm reading lambda.
Okay, so tell me, what is your arc here?
It's lambda xmx, and I'm pushing S.
Okay. So you are using the grammar.
Yes.
Okay, and the second one is?
Lambda yy, and I'm pushing M.
Okay, so you started by first obtaining the context-free grammar for palindrome, right? So your grammar should say something
yes,
like
I thought like this.
X, well, you did you used M, and maybe you use them something like this.
Yes, like this.
Okay, well, yes, it's correct to think on the grammar and then try to do the push-down automaton. However, for this case, the correct grammar would be S, and then for each X you insert, you need an X at the right side, and then for each Y you insert, you need a Y to the right side, and finally S can be lambda, because you can avoid using it at any time. So this would be the grammar for recognizing a palindrome, because you are, whenever you have an X to the left, you need to add an X to the right. Whenever you have a Y to the left, you have a Y to the right, and you can just stop adding S. You can add M as well, but you will just add more rules. Because if you add, for example, here M, then you have to do again M for X and M for Y. Yes. Okay, so following your approach, supposing that you are trying to substitute these kind of things, then yes, it is possible. But you need to add the mechanism for adding S magically to make it appear. So let me finish building this as your original idea. Now I get it. So we just need to follow these rules as we had before. We would have lambda, and then X is X and consuming S, or lambda Y is Y and consuming S, and finally the magical way of just inserting an S. Why? Because we have this transition. And finally, consuming the S, and finally consuming the hash. Okay, so this would be another possible solution for this problem when you start from the grammar and then convert it to a push-down automaton. So it's correct. Oksana, your approach is correct. And we can see also that this solution is very different from the one that Oscar and Cesar presented to us a few minutes ago. But both of them are equivalent and both of them are right. Now I see Arturo wants to show his solution. Okay, so Arturo wants us to have a complicated thought, but it's okay. Let's check if it's correct. Let me try to, don't move. Make it a little bit farther, please, Arturo. Okay, not so much. Don't move. Okay, let me see if this works. Well, not quite sure. Now you can see how I suffer when I see your automata. So let me try to reconstruct this, and you will let me know if this is correct or not. So you used a marker like an @ symbol. This is an X, and this is so I cannot see this symbol. What's that, Arturo?
Is Y.
Yes.
Symbol of pesos.
Okay.
And lambda.
Okay. So whenever I don't understand, then it will be a dollar sign or a pesos sign.
Yes.
And here we have, ooh, is this correct?
Yes.
And the left one is y lambda pesos.
Yes.
Okay, so now we need to program a neural network to convert these almost invisible images into a correct push-down automaton. But it's possible, it's possible. Okay, so let me try to understand, because on principle this is quite complex, but it might be correct. And also here we have x, lambda, at. Okay. So whenever you see an x, you are adding an at, which is correct, and then you keep doing that.
Yes.
And also, if whenever you see a y, you will use a $sign, which is also correct, and keep doing that. Whenever you have an x, well, you will change onto this one and keep adding this, or if you change to y, you keep doing this as well. And finally, at some magical moment, instead of adding you start removing them, or the same with pesos here, and then you keep doing this and this until you finish. Well, yes, I think this solution is correct as well. It's a bit redundant, this part maybe, because you don't need to do that much. Because you don't need to differentiate one state or another, because you can just be receiving x and adding at symbols, and receiving y's and adding peso symbols, and then you again magically can change. So let me try to redraw this by using the lambdas and the at symbols and the pesos. I like the pesos. Maybe it's good luck, and we can have a lot of pesos in our pockets.
Yes.
And well, so this would be, following your idea, you just keep receiving x and then adding an at symbol, or you receive a y and adding a pesos symbol. So you can see here, you don't need to differentiate, because you can just keep adding, and it doesn't need to be a different state. However, this way of thinking can be useful when you really do need to differentiate. Not in this case, but in others might be. Now, your mates did something interesting here, because they suddenly added a lambda transition, which does the magic of changing the state from adding or pushing into the stack, and then magically changing to consuming from the stack. So this is right, but also following the way of thinking of Arturo says, okay, I don't want to use this magical lambda transition, because I can just start, instead of inserting, I can just start consuming like this, or I can just start consuming pesos like this. Yes. So by this means, you are not using a lambda transition, and the effect would be almost the same. And then you change into state that when you have reached it, you don't have to go back, because you can just start consuming symbols the same way as before, like this and like this. And finally, accept the consume the hash from the stack. This is almost equivalent, and I want you to ask, I want to ask you, what is the difference between this and the solution that was presented before? If you want, I can draw it. Try to draw it quickly. Last time when I recorded this video and then I replayed it at 20 times faster, I said, oh my God, my class is so slow. But I don't know if you have the same feeling, that maybe we spend too much time writing some things. But well, I hope it's clear for you. That's it. So the difference between this and this is just the magic transition. Well, I call it magic just because it's a lambda transition and you can choose it whenever you want. And if you don't want, you don't follow it. So it seems like perform some kind of magic. But of course, there is no magic here. So these and these are almost equivalent. Can someone tell me in which case they are not equivalent? Let me give you a short tip. When you are examining the possibilities, you start examining by the shortest string. What is the shortest string that can be accepted by one and not the other?
An X, for example.
Okay, but we said that we would restrict to odd number, to odd palindromes. So an X wouldn't be in this scheme. But let's say we can begin by XX or YY. Yes, however, there is something shorter.
Lambda.
Yes, and there lies the difference. So what happens if we want to accept lambda, the lambda string in one case and in another case?
In the first case is not accepted.
Right, and the second one is accepted. And what about your automaton, Arturo?
It doesn't accept it.
Also, it doesn't accept it. Right, that is right. So, well, we can fix it. I mean, we can just add, for example, if we don't want to use lambda transitions, well, we can do this accept. We can do an accept state, this as well. And that's one way of fixing it, right? Another way of fixing it, if we don't want to add an accept state at the beginning, is saying, okay, you can reach the accept state just by consuming the hash symbol we have just added. That's another way of fixing it. And then now they are, the three of them are completely equivalent. Now they are. Now this, and let me go back, sorry, because I want also to rescue this one. I want to get this one into scene and put it as well. Okay, now we have four beautiful different ways of solving this problem. And all of them are completely equivalent. And I like to stress this as well because you can see there is not a single solution, right? There are, when you are faced to an open problem such as draw a push-down automaton that accepts this language, you have so many options. And also I am glad to see that you were able to visualize different ways for solving this. So I think this is very good, as You can, as we say, several heads think better than just one, because you came up with different solutions to this problem, and that's okay. Now, perhaps with some experience, you start having some solutions that are simpler in terms of, for example, number of arcs. This is the simplest one, I would say, because it has less arcs, and maybe it's is more readable, I would say, like in programming, right? You can program like using very difficult structures or easier ones, but all of them are correct. Okay, now let's do another exercise. Yeah. Okay. So this now the exercise will be find a push-down automaton that accepts the following language. Let me use exactly the same that comes in the textbook so that you can check it afterwards if you want. Let me see, this should be exercise number 1, I think. Yeah. So now we have to do some operation. S is equal to R plus T, meaning that this S that is in the middle should be exactly the same number as R and T. So let's see some examples. In this case, does this language accept the lambda string? I think Sarah says yeah, right? No? Oh, okay. If R equals 0 and T equals
I think that we are not seeing the yeah. No. Okay. Yes.
Thank you. Then it's possible, right? If R is equal to 0, T equals 0, and S, which is the equation, equals 0, 0 plus 0, and then this is correct. And also we are stating that 0 can be included as RST. So yes, the answer is yes, lambda is here. And of course, there are other strings. Let's write some possible examples. For example, what if R equal 1 and T equals 2? Then S should be 3. Then this string X, Y, 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 Z, Z is included into this language. If we change something that doesn't add up, then the string is not in this language. For example, X, Y, Y, Z, Z is not in the language. X, Y, Z is not in the language. Let's say X, Y, Y, Z is in the language, or even X, Y is in the language, or Y, Z, right? What about XZ? Is XZ in the language? No, Oksana says no. Okay, and everyone says no, right? Very good. So this is not in the language. Okay, very good so far. Now we understand a little bit more how this language is. And now we are asked to let me move this. Now we are asked to do a pushdown automaton that recognizes this. One way, of course, is to think of the grammar. I think it's a bit complex to see what the grammar for this is, and maybe we can try to build it step by step. So by building it step by step, we need, of course, to add the hash, because we need to count that the stack ends up empty completely, because we need to verify this. And then we will have two different operations. I will just make a block diagram. First, you start adding symbols to the stack for each X. And then you start consuming for each Y. And finally, if we think like this simple, we need to, again, add symbols for each Z. However, we will have a problem with this, because whenever we have something like X, Y, 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 Z, Z, if we do it in this simple way, we would have, let's say our symbol is an at. So we add this, and then for the X, we add the at symbol. For this Y, we consume this, and then we cannot consume a Y after this. Why? Because there are no more at symbols. Then, whenever we cross the 0 border, then we need to shift our operation. Now, instead of consuming, if the hash is reached, then we change our operation, because now we are not consuming symbols. Now we will be adding symbols for Y. And then, of course, the whole operation is changed, because now we will consume symbols for Z. And if any case, if we reach the hash again, then we reach an accept state, which in this case is strangely squared, because this is just like a block diagram. I want just to give you this so that you can try to build it properly with rounds and sticks. I don't know how you say in English, but in Spanish we say palitos y bolitas to say what we do when we are learning to write. So it's like we say stick and we say ball, like writing like this. So it's like a very basic thing. Okay, well, not important. So now please change this block diagram into the proper pushdown automaton that will recognize this language we have here. Oscar, please go ahead. Okay. The right part is still missing, so make it a little bit, not the, well, the left part then. Make it a little bit far away. Okay, now move to the, okay, that's it. I have it. So let me check it here. So it's start and then add a hash, then and then add x y at y. What symbol is this? Lambda? I'm afraid I cannot hear you. What is this symbol, Oscar? This. Here.
Which one?
Here.
Is, yeah, it's y and lambda.
Okay, so please check it if it's right. Is this correct, Oscar?
Yes, it's correct. Well, that's my
So in this
solution.
case, you're assuming that when you see a y, then you consume an add symbol and insert a y into the stack, right? Okay. Same as this. Okay, I see. Okay. Okay. Okay, I think it works. And the only problem with it is the zeros. Whenever you have 0R or 0T or even 0S, it won't accept them. However, for different numbers than 0, this is okay. Okay, Christian, please. Let's see. Here it is. So you add a hash here, and then for each X, you add an @ symbol. And you are missing here, what is the, no, it is this one. Okay, now I see it. Okay, so if you have an X, you start adding X or @ symbols, you start consuming them, and suddenly, magically, you change, and that change would be producing, okay, and start producing, and finally, when you see the Z, you start consuming until you finish. And I think this, we just indicate you have 0x, then you add this @ so that you can receive the corresponding Z, and then move here, or even having 0 everything, you are just consuming the hash. And if you have X, let's say an X, and then you have a Y, then you can pass here. Okay, okay, Christine, I think it covers all cases. It's correct. Arturo, okay. Oh my God, it's very complex again. Let's see. And also let's see if I'm able to see it. Okay. Okay. Let me see if I can get a better picture of it. Don't move, don't move, don't move. Still don't move. Let me see if I can change the view to a single one. Okay, that's much better. That's it. Okay. So you add a hashtag, then X and a symbol, or consume. You keep consuming it until you reach, yes, you are verifying through the hash. I think that it might be a problem for the previous one. The previous one was Christian, right? Maybe with Christian, because you are doing the change, like a magical change, by using a lambda transition, instead of checking that you have reached already the hash, might be a problem. We can come back to this later. We will check that. But well, in this case, you are checking the hash, and then what is this? You are checking again the hash, Arturo, but there is no hash anymore.
I'm actually adding a hash again.
Yeah, I think you should write here this. I think that's your mistake here. And now that you do this, okay, then you you start using, so you like pesos a lot, okay. Then, yeah, it's correct. It's correct. And also you are adding bridges as well as Christian for allowing to accept. Maybe what happens if you have 0 of everything? Maybe that one, the last one, 0x, 0y, and 0z.
0x, I think it's accepted because uses the first bridge with the y.
Yeah, but no 0x, 0y's, and the 0z. This. So just that one is missing here. But the
Okay.
other cases, yes, you have considered it. Cesar, please. Let me try to capture your screen. Don't move, don't move, don't move. Don't move, don't move, don't move. Oh my God, I lost you. Don't move, don't despair. I'm capturing it. Okay, I have it. So here it is. So Cesar is adding here. Then in the same state, you are adding X and consuming them. So this is a problem, Cesar, because if you do this, then you allow to change X, X, and then Y, Y, something like X, X, then you consume this to X, then you can add again to X and go back. And you can see that the language does not allow to have to have again an X here once you had Y. So this shouldn't be accepted, and in your solution you are accepting it. So you need to check this, Cesar.
Okay.
Okay, so as we said before, we were coming back to the solution of, I forgot who did the solution, but Christian, no, or the one before Christian. Okay. Okay, yes, this is the magical transition with lambda over there. What happens there? Let me see. X, Y. I think, who did this? Please remind me. Did you do this, Christian? Or who? Okay. The problem of using this is, I think it allows these kind of strings, like X, X, Y, Y, Z, Z, Z. Why? Let's try to process it. So we have the stack here, our head is here, and we add the hash, and then that's it. We start with X and we add an add symbol. Then for the next one, we add another add symbol, and then we have the Y here. Then for this Y, we remove this add symbol. So we are standing here, right? And then we magically change, because we change here. And now for the second Y here, we will add an add symbol instead of consuming it. And then we will be able to repeat 3 times Z, 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 or not even 3 times. I think only 2 times. That's it, 2 times, Z, Z, and then finally take out the hash and accept this string, which is correct, right? No, it's not correct. It's X, X, Y, Y, Z, Z, and shouldn't be accepted because R equals to Y, and S equals R plus T, and T equals 2. So S should be 4. So what is the problem, Christian? The problem is that you are allowing this change without checking that we have reached the bottom of the stack. To check the bottom of the stack means that you should ensure this change is given, is done only when you have reached the hash. You can do this, for example, in a single transition. Let's suppose you want to check if there is a hash on the top of the stack. You can take it out and then put it back in. Or you can do it in several transitions, just as Arturo. Arturo first take it out and then in another transition put it back. Or you can do it in a single transition. It's the same. Yes, but both are okay. So be careful with this transition, because in this case it seems to be correct, but because of this transition we have problems. We're accepting strings that we shouldn't accept. So I think Cesar has raised his hand again.
No, sorry.
Okay, then it's the last hand. And now Christian, the other Christian, has raised his hand. Please go ahead, Christian.
Yes, I already sent you my solution using the chat.
Okay. Let me see. Checking solution in the chat. Where is the chat? Here is the chat. Okay, thank you. So following the projection of all solutions sent, thank you for sending me the solution. And we have something like this. Okay, so we have first, we are adding a hash, then for each x, adding an add symbol until we find y's. Then for the y's, we start consuming them until we reach the hash. And then whenever this happens, we start, instead of consuming, we start adding until we find z's. And for the z's, we start consuming until we find the hash again, and we are able to take it out. Yeah, very, very nice. This is a good solution. However, there is just something missing. What happens, for example, when we have 0 y's, or when we have, I think that's not possible. Yeah, when we have 0 z's, or when we have 0 x, which are valid, and also when we have the lambda string. So just check that, please, Christian Jaime. But the rest is very good. I think it's a very straightforward solution because it's straight and goes forward. Sorry for the bad pun.
Okay, thank you.
Cesar, okay, again, very good. Let me again capture your screen properly. Just give me a second. So this is the second solution from Cesar. Let's see what happens. It says hash. Oh my God, what happened? Okay. So hash, then at this, okay, then a magical transition when we start consuming y's. Okay. And then whenever we find, and suddenly we take out and add, and then put it back again. But I think there is something missing here, because when you are consuming these add symbols from Y, and then you need to keep, when you change the mode, maybe it's this one. If you reach, I think it's this one. When you reach this one, then you start adding instead of taking out, and then you change to the Z until you are able to find this. And by using these lambdas, you ensure that you can travel lambda, check the hash and lambda, and finally take it out. Yes, yes, it's correct. And just in case this strange thing happens, you can just continue doing this in case you don't have, maybe let's say X. I'm concerned with this one. Because it allows something like
the case is when in the diagram with the squares, you said that we add symbols to X, then consume symbols for Y, and then we add symbols for Z in case we don't reach the hashtag.
Okay, okay.
So if there are still symbols from X on the first two stages, like X and Y, there will be still some adds at the stack.
I see. Okay, so this is just to empty the stack. However, you reach an accept state, and let's suppose you have the XZ string. So you will add an add because of this transition. You have this and you have this, and we are here. And then you don't have any Y's, and then you, because of this, you are just removing this add symbol, and then you are putting it back. And then you read the Z, and the Z removes this this add symbol, and then you move here, and finally remove the hash symbol, and you accept this string XZ, which is not correct, because as the language says, we must have you can have XY or YZ, but not XZ, because if you see like XYZ, this is R, this is S, this is T, and S equal R plus T. And in this case, R is 1, T is 1, and S should be 2.
Okay.
So the string is not correct.
So now I have a doubt.
Yes.
That last stage, it's not an accept state. It's
yeah,
like
yes. Or because I think you want to empty your stack, then this is a good alternative to empty your stack, and then just you don't make this an accept state, and that's very, very good. Or even you can just remove this from your diagram, and it's completely right, and maybe you will end up with a non-empty stack in all other cases.
Okay.
And yes, you are right. You did this because in my square diagram, I added this part. So that's why you wanted to add. I understand that. But then you have, I think you have understood properly.
Okay.
Very good. So yeah. Okay, so I think now you have the correct solution. And I want to change to different subjects. Just before we finish, I want you to keep practicing this at home. So I will give you some homework. Wow, that's a bit horrible, but okay, homework. Again, just a simple homework, because I think you have a lot of homework from other subjects as well. So let's take page 132, exercises 3 and 7. So exercise 7 is very nice because it's very similar to the thing that we have been doing today. However, it's just a little bit more complicated because it adds another variable. So there's number 7. This is it. Now you have one more letter and you have to check 2 different conditions. But I think you can do it with what we have seen today. So go for it. So this will be for Tuesday 11th. 6, 7, 8, 9, 10. Yeah. And same 55. And the previous homework you will have until Friday because I should have opened for today. So previous homework, please upload it by Friday and Friday's night. Okay, so we have 25 minutes, so we can see last subject. Let me show you. So this is quite a simple automaton, push-down automaton that accepts something very simple. Actually, it uses the stack, but it uses in a very basic way. Actually, what this is doing is accept a C, and then any number of B's without taking into account the stack, and then recover this C. Of course, there's no need for using the stack, right? We could just have written the same one by using just deterministic finite automaton. Actually, the stack is not needed for this one. However, is the example that Brookshire gives to us in order to illustrate how to obtain a context-free grammar from a push-down automaton. So we began this class with showing how easy it was to do the reverse thing. In this case, these 2 diagrams. And well, I think it's pretty straightforward for you just to take a grammar and draw a flower and do this. However, the reverse, like obtaining the context-free grammar out of a push-down automaton, is not so straightforward. So let me introduce you this with this example. I will give you the procedure. And first we have to do is, this is taken from page 93, in case you later want to check it, of the Brookshire book. So first we need to add a rule, which is S goes to, and we will add the initial state that in this case is F, and the final state that in this case is H. So I will tag this. This is initial state and goes to final state. And I just want to show you also that these triple things are just a non-terminal symbol. Remember that non-terminal symbols, we usually use a capital letter. So you can imagine that this M can have subscripts just like F, lambda, H. And finally, we just write them like that. But actually, all this is just a single non-terminal symbol. Just as if we write S, M, or P, or anything with a capital letter. Why we are using this triangle notation? Because we will need, we will have different ways for building these rules, and in order to make it a little bit less complicated. Okay, so first we add one rule. This will be just one rule. Then for rule two means add one of these rules for each one of the states. So for each state, add a rule. So we have F because we have an F here, G because we have a G here, and H because we have an H here. So if we had 10 states, we should have 10 rules like this. Because we have 3 states in our example, then we will have 3 rules here. So this is one, or we have 3 states in our example, F, G, H. Okay, so so far, so good, I think. No problem with this. Then we will have for every transition G, C, C, H, and lambda, we need to see what transition is this one. This is referring to the transition G, C, C, H. First, we need to understand how this transition is being written. First, this is the origin, the state of origin. Then this CC, this is the symbol read from string. And then this is symbol from stack. This is state of destination. And finally, this is insert into stack. So let's write it again. If we have, for example, G goes to H, and we have C, C, or let's put it differently. Let's put it more general. We have a state P and a destination Q. And we have a symbol from the string, which is, let's say, A, and then we have B, and then we have C. Our transition would be from P and reading A and B, go to Q and insert C. So this is the general template for giving these kind of transitions. So given that this transition is this one we have here, you can see in this case, C is this C, this is this another C, is this C, finally destination is H, and this lambda is this one. So rule number 3 says the following. For each transition of the form P x lambda Q Z, generate all rules with the form P W R produce X Q Z K K W R, where W is either a stack symbol or lambda, and K and R belong to the states of the machine. What does this mean? That we will generate sorry. This is rule 4. So let's keep this for the future. Sorry, we will use this, but this is not the real rule 3 we are illustrating. So I will just move to the second page. Sorry for this. Okay, so we'll use this here. Okay, again, so rule 3 says for each transition P, A, B, Q, C, add a rewrite rule or a rule which says P, B, R, A, Q, C, R. That's it. So please observe that we have PAV and QC is the same one, PAV, QC. So we are talking about a transition. And our rewrite rule will be from P to Q, and this V is the same symbol as this one. And R will be all states, is a state of M. We have 3 states, so we will iterate this R through F, G, H. You can see here, this is precisely iterating F, G, H, F, G, H for this R and for this R. The rest will remain the same. P, in this case, P for this transition, which is this one, will be G. So this goes from P to Q, which in our example is from G to H. Every time we say P, we will change for G. Every time we say Q, we will change for H. So if it says Q here, we will write H. And then A. A, following our pattern, is in this case C. So all A's will be C. And again, here we have an A, we will have a C. And finally, our last one, C from this pattern, is this one. So is this lambda, and this, it will be lambda, lambda, lambda. So don't worry, maybe I'm just pointing a lot of things at the same time, but what we are doing is very simple. We are just taking some variables and using this into the template. So this is a template for adding a rewrite rule, okay? So we have 3 rules here, just as before, because we have 3 states, F, G, and H, and it says for every R, when R is a state of M, we need to iterate this. And which rules we will be using? We'll be using all rules that are not lambda here. So this is very important. This is not lambda. In this case, this is the only transition that complies with this condition. In this case, lambda, there is a lambda here, there is a lambda here, so we'll apply rule 3 only for this transition. Because we will use rule number 3, which is, this is rule number 3, only for transitions that where this is not lambda. So rule number 3 won't be applied to this or this one. Yeah. Okay, so there are just 4 main rules. We have seen rule number 1, rule number 2, rule number 3, and there is just the last one, rule number 4. And probably, as you have seen, all rules, all arcs have been covered this, but we have not covered this and this. So rule number 4 will apply whenever this is lambda. So in the next case. So let me turn the page and show you how this applies. Let me move this here. Or maybe I will just redraw it. Okay, so you can see there are a lot of rules here. How do they come from? Well, I put it the rule a little bit, so it will be for each transition of the form P, A, Q, C. Remember, we have our P and A, B, C, and Q. This represents this thing. Now, we are forcing this to be lambda. So in this case, we won't have B. This needs to be lambda. Yes. So for each transition of this form, we need to add rules with the form. I will put it just below so that they align and are easy to understand. P, W, R, A, Q, C, K, K, W, R, where W belongs to stack symbol or lambda, and K and R belong to S, which are the states of the machine. What does this mean? That we need to iterate for each K and then for each R. So we will see where is K. K is here and R is here. So if we iterate before on R, we see for each R, F, 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 G, 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 H, H, H. And then for each K, K is here and here. So you will see FJH, FJH, FGH, 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 and finally FGH and FGH. So here we are iterating over R, and here we are iterating over K, having all the different combinations: F, 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 G, F, H, G, F, G, 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 H, H, F, H, G, H, H. So we are just iterating, having all the possible combinations. And finally, we repeat this because now we need to iterate over W. And W says W is here and here. And then we have here is W and here is W. And then here is W and also here there's W. Yes. And what does this W mean? It says W is all the symbols from the stack. So let me just go back quickly here to the diagram of our automata. I will copy this to the next page. So if I take it, it's easier to see. Okay, we have it. So you can see that the symbols for the stack is only C and lambda. So we need to iterate for all the symbols that are C or lambda. So the part that is in yellow is W and W. Yes, and this comes from this rule. So we will do this for this transition FC lambda GC, which is this one, FC lambda GC, goes from F to G using this transition. And now there is a last transition which goes from G to G and using B lambda lambda, which is from G to G and using B lambda lambda. So this is this transition, and we will do exactly the same. We will start iterating for all F, 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 G, 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 H, H, H. F, and then we will do FGH, FGH, FGH. And again, we have F, 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 G, 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 H, H, H. Remember, this is R, and this is K. Also, I forgot here to do this. This is K, and this is again R. And these are the R here, the K, K, R. Again here, R, K, K, R. So R equals R, K equals K. Again, FGH, FGH, FGH. And finally, we will have also the W. In this case, W equals lambda, and in this case, W equals C, just as before. So that's why we have so many rules, because we are just applying these templates first for this transition, the green one, and then for this transition, what color is that? The orange one. And we need to iterate through all combinations of R and K, and of course P and Q remain the same. P is always the same because it goes from G to G, and Q also is G, G, G always. G, 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 always the same. And finally, with all these rules, we will have our grammar rules corresponding to this very simple automaton. So you will say, how come? Why so many rules for something that is so simple? Well, because we need to generate all the possible rules, and next class we will see that not all the rules are used. We will see how this works on the next class. On the meanwhile, please study it, and because it's a very cumbersome procedure, I don't want you to be struggling with this in the exam. However, I will ask you to program it. I think it's quite easy to program it. I will give you more details in next class for programming it, but it's just a substitution of rules. The main thing will be on how we describe this kind of automata, but it won't be very hard, so don't panic. And also, in the meanwhile, I need to announce you that we are about to finish this chapter as well. So next Tuesday will be the last class for this chapter 2, and so that next Thursday we will have an exam regarding this subject. So please check your homeworks, check your questions, because if you have any doubts, please come next Tuesday with questions so that we can answer them, and you are ready to present the exam next Thursday. Regarding the program, of course, you will have enough time to finish it. It will be for around mid-June, the program. Okay, so time is over. Again, if you have any question, please write to me at Telegram or at the Moodle system, and I will try to open as soon as possible the slots for uploading your homeworks. Thank you for your attention. I hope this class wasn't too heavy or too boring. So have a nice evening, no, a nice afternoon still, and enjoy. Thank you. Bye-bye.
See you. Have
Thank
a
you.
nice day. Thank you. See you.
Thanks.